This video is on graphing relationships. We can compare two variables using a graph. The key to being good at reading graphs is reading the labels and trying to understand what's going on. Our first example is titled Angelica's Heart Rate. We can see that on the horizontal axis, which is here, horizontal axis, that it's labeled time and the units are minutes. The vertical axis is labeled heart rate and BPM stands for beats per minute. For example, your heart rate when you're sitting and you're calm might be around 60 to 70 beats per minute. All right, and then we have this shape. Kind of starts out sort of flat, it climbs up, it flattens again, it comes down, and it flattens again. And what we might want to do is describe what's going on with Angelica's heart rate. So it's constant at first. Constant means flat. So this that I'm tracing over in red is flat. So maybe that's 70 beats per minute. And then let's say she starts jumping up and down. Well, that's going to make her heart rate increase over time. And then she may reach what's it called? Like a maximum fat burning heart rate. And she sustains that for a little bit of time. And then she stops jumping up and down. Her heart rate slows until it's back to the resting rate, and then it just continues until she does something else. So that's an example of a graph. Now I want you to notice something. If I pick a particular time, like right where I'm putting this red mark, let's say this starts at time 0 and this is time 1 minute right here. Well, she has a particular heart rate at that moment in time. If you took your pulse right now, you would find that you have a particular heart rate. You can't have two heart rates because you only have one heart. So then if you look at 2 minutes into our little time passage, you'll see that Angelica has a different heart rate, a faster heart rate, a higher heart rate. But she only has one heart rate at that particular moment in time. This is a characteristic of a function. So if you know when you're measuring, then you'll know from the graph precisely what the heart rate was. All right, let's look at another example. This example is a child going down a slide. And I'm going to use this example to emphasize the importance of reading the labels on the sides of the graph. On the one hand, we have a graph with a horizontal axis labeled time and a vertical axis labeled distance from the ground. Now, when you're getting ready to slide down a slide, you are obviously a few feet off the ground. So at time 0, the child is going to be some distance from the ground. So this would be ground level, that horizontal axis. So the child's on top of the slide. Now, when they push themselves off, their distance from the ground is going to decrease, usually rapidly, because the slides usually start out pretty steep. And then there might be like a curve in the slide, and then another steep part, and then the child is back on the ground. So here we're comparing the passage of time to how far above the ground, probably measured in feet, the child is at any particular moment. Well, compare that graph to this graph. We have time again on the horizontal axis, but this time the vertical axis is labeled as speed. And let's say that speed measured in feet per second. It usually just takes a few seconds to go down a slide. At time 0, the child is sitting at the top of the slide and they're not moving. So at time 0, we have speed 0. Then the child pushes themselves forward, which increases their speed slightly. Then their speed increases rapidly. And then they might hit that spot where the slide sort of levels off, which will make them slow down. And then they'll continue slowing until they hit the ground at some time in the future. Now you can see that this is the same situation, a child going down a slide, but the two graphs show very different things. Now realize that the distance from ground graph more likely represents the actual shape of the slide. The speed graph does not tell you the shape of the slide. It tells you that the speed increased and then decreased, and then the child hit the ground and they stop moving until, of course, they run around and do the slide all over again. Notice another characteristic. If you pick a moment in time, like right here, there is one point on the graph that represents the distance that child is from the ground. So let's say this is time 2 seconds. So 2 seconds in, the child is a few feet off the ground, and they can't be in two places at the same time. Same thing with the speed graph. If I pick a time, like 2 seconds in, the child is traveling at a certain speed, maybe 3 feet per second or something like that. But there's only one such point. This is a characteristic of what we call a function in math. One more thing, I want you to notice something so far. In these quote-unquote real-life graphs, it's very, very common to see time on the horizontal axis. Now, the horizontal axis is used to represent what's called the independent variable. So think of the independent variable sort of as the driver of the problem. Time is passing, whether we like it or not. It's independent of what we want or what we're doing. It just keeps ticking and ticking. The other variable we're measuring is called the dependent variable. So listen to this language. My heart rate at any particular time depends on that time. So my heart rate at 1 minute in is 70 beats per minute. My heart rate at 2 minutes in is 115 beats per minute, for example. So my heart rate depends on how much time has passed. Same thing with both of these slide graphs. Time is independent. We don't control time. It is what it is. It just keeps on ticking. The distance from ground depends on how much time has gone by. Once you kick yourself down that slide, time is in charge. You're going to go down the slide, and gravity, I guess you would say. Same thing with speed. At a particular time, you're going to be going at a certain speed. So the passage of time results in different speeds because you're at different places on the slide. All right, another example. This time we're going to create a graph. Here's the situation. Bob is filling a swimming pool. So let's just draw a picture instead of writing all those words. So it's an above ground pool, and Bob has 2 hoses going into the pool because he's in a hurry. So we have, it's obviously a clear pool because you can see the water level. So these are two hoses filling the pool. Well, then Bob's wife comes along and she takes one of the hoses to water the garden. Now, let's look at the water level. When there are two hoses going full blast, filling the pool, the water level is going to rise fairly quickly. But when Bob's wife comes along and takes away one of those hoses, the speed of that water level change is going to slow down a lot. So let's try to represent that with a graph. I'm going to put, surprise, surprise, time on the horizontal axis. And we're going to measure water level on the vertical axis. Now remember, for the first several minutes, so clock is ticking, tick, 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 there are two hoses filling that pool. So the water level, which starts out at 0 because there's no water at first, is going to rise pretty quickly. But then along comes Bob's wife, and she takes away one of those hoses. Well, the water level is still increasing because the one hose is still filling the pool. However, at that moment, there's a turn or a corner on the graph, and now the water level goes up more slowly. Okay? All right, let's look at another example. We're going to create a graph again. This one's about Charlie. Charlie is eating 3 hot dogs per hour for a 5-hour period. That's gross. 3 hot dogs per hour for 5 hours. We want to graph the number of hot dogs Charlie eats versus the time that's passed. So we're going to say number of, I don't know how I did that. Go away. Oh, dang. Okay, there. Close. So we're going to do number of hot dogs versus time. Now, guess what the independent variable is? Time. We have no control over time. It just keeps on going. So this is time. And because he eats 3 hot dogs per hour, we're going to measure time in hours. And per hour, we know how many hours, 5. So we're going to say this is 1 hour, this is 2 hours, 3 hours, 4 hours, and 5 hours. The vertical axis is going to be the total number of hot dogs. At the beginning, Charlie has eaten no hot dogs. After 1 hour, Charlie has eaten 3 hot dogs. Now, notice what I didn't do. I didn't draw a line from 0 to that dot. I didn't connect those like this. Because it's not like you absorb the hot dog sort of continuously over that first hour. There's 1 hour, he's eaten 3 hot dogs. After 2 hours, Charlie has eaten 6 hot dogs. After 3 hours, he's eaten 9 hot dogs. Notice how the dots are going up by 3. After 4 hours, he's eaten 12 hot dogs. And after 5 hours, he's eaten 15 hot dogs. Notice how this particular graph is a bunch of dots. That's because you can't continuously absorb the hot dogs over time by like laying on them or something. In the previous example, the water level graph, we have lines connecting everything, and that's because the water actually does fill continuously You know, like there's an inch of water, and then there's like an inch and an eighth of water. Then there's an inch and a fourth of water, and the water just keeps rising continuously. Hot dogs are like things. They're chunks. This is called a discrete graph. Discrete graph is a bunch of dots, and we'll learn more about this in a later video. All right, another example. In this example, let's see, we're going to create a graph again. It says you walk due north to the park at a constant rate. So you're just your normal walking speed. You don't speed up, you don't slow down, you just, walking due north at a steady rate. On your way there, you sit down on a bench and you rest. Okay, so you're moving at a steady rate, then you stop moving and rest. Then you jog due north 2 miles. Then you walk slowly home. So let's kind of write this down as a sequence. Step 1, walk steady. Step 2, sit and rest. Step 3, jog 2 miles. So we jog for some time. We don't need to know the mileage really. And then we walk slowly. Sort of implies slower than any other time. Slowly home. We're going to draw a graph allowing time to pass on the horizontal axis. And there's a lot of things we could measure here on the vertical axis, but we're going to measure how far you are from your house. Distance from home. All right, now you started out walking from home. So at time 0, you were at home. You walked at a steady pace. That means your distance from home went up steadily. Maybe sort of like that. At some point, you stopped and you rested. Now, does time stop just because you stop? Time does not stop. So your distance from home is going to stay the same the whole time you're resting. Notice time is passing because we're moving to the right, but distance from home, this like y value, is staying flat. So after you're done resting for a certain period of time, you jog 2 miles. Now when you compare walking to jogging, obviously jogging is going to help you cover more ground at a faster rate. So now you're jogging. So we're going to make this line steeper. All right. Now it doesn't say that you actually stop at the park. It says that you then walk slowly home. So you're turning around now and you're walking due south slowly home. Remember, time is still passing. So from this point right here where I'm sitting, I can't just go home like straight down. I have to walk slowly home, which is going to give me my distance from home gradually gets lower. Okay, so here's where I'm back at home. So this is the walk, this is rest, this is jog, and this is walk. But this last line is supposed to be less steep than the first line. I'm not sure if I've actually accomplished that. But notice again that if you pick a time on this graph, like say that where this red X is, that's my time. If I'm interested in how far I am from home at that time, well, I can find it on the graph. There is only one, I can only be in one place at that particular time. That's a function. Okay, last example. The number of visitors to the town park decreases by 2 each day for 7 days. So decrease by 2 each day for 7 days. All right, let's check this out. If it's decreasing by 2 each day for 7 days, that means we must start out with, at times 0 with a bunch of people. Boom. So this is number of visitors. So we start out with a certain number of visitors. Then, let's see if this is one day, I have 2 fewer visitors. And then another day goes by, and I again have 2 fewer visitors. Another day, 2 fewer visitors. Another day, 2 fewer. Another day, 2 fewer. Another day, 2 fewer. How am I doing? 1, 2, 3, 4, 5, 6. This is the 7th day, and I have 2 fewer visitors. You can see the number of visitors is just like a number. It's like if there's 7 people, there's 7 people. There can't be 7.5 people. So again, I get these very specific and separate dots that measure the number of people. This again is a discrete graph. All right, this has been a video on graphing relationships. Thank you for listening.